Hello everyone. In this video, I am mainly going to be talking about end behavior and function composition. We're going to cover a very important limit table along with that, some domain questions and function composition. So let's dive in. Now, whatever device you're on right now, I want you to take a note of this. Just take a photo, take a screenshot, or write it down in a notebook making a small table. This is that important, okay? It tells you about the end behavior of a polynomial function just based on the leading coefficient and the degree. And you'll have at least one question in your MCQs in both the sections about this on this topic. So I want you to get very thorough with this. It says that if the leading coefficient is positive and the degree is even, then the graph rises on the left and the right. You'll have something like this, okay? It's rising on the left and rising on the right. That is the essence of rising on the left and right. If the leading coefficient is positive and the degree is odd, then it says that the graph falls on the left, and rises on the right. It's rising here, falling on the left. If it's negative and you have an even degree, it's going to fall on both ends. It's going to fall like this, okay? If the leading coefficient is negative and the degree is odd, we have rising on the left and falling on the right, something like this. Now, there is no explanation for this. You just have to note down the table and remember for what combinations of leading coefficients and degree does the graph rise or fall on the right or left. That is the only thing here. If you ask me on how to remember it, there's not much of a pattern here. Just know that if the leading coefficient is positive, then it will rise on the right. And if the leading coefficient is negative, then it will fall on the right hand side. This is the only part that you can logically remember. The rest of it, you need to by heart it. I'm going to show you one application now. Now, what you have on your screen, the question, state the end behavior of the polynomial minus 4x cubed minus blah blah blah. We'll look into that later. This is not exactly how the question might appear on your test, but it's somewhat similar to what might come, and the essence will remain the same. Now, in order to find the end behavior, I'm going to first write it down. We have minus 4x cubed minus 17x squared minus 14x plus 6. First of all, pick your term. We know this is the term which has the leading coefficient and the degree. We know the degree is 3. So first the coefficient will be negative, and the degree that we have here, which is 3, is odd. And according to the table that we made, or which has been given to us, we see that if the leading coefficient is negative and the degree is odd, it's going to rise on the left and fall on the right. Rise on the left, fall on the right. It's going to be something like this, as already showed before. Rise on the left, fall on the right, and yeah, that's it. They might ask you something similar to this, or they might do the reverse. They might give you a graph and they'll say, find a possible polynomial for this graph. In that case, you go the opposite way. You look at the possible coefficient and you look at the possible degree. Let's move ahead. Now, function composition is something that is quite important from the test perspective. We're going to have one MCQ or two, and the FRQ one has some part of it on function composition. Let's look into it. It says that two functions may be linked to form a new function by using the output of one function as the input to the other function, and the new function is called a composite function. Given two functions f and g, and then the composite function denoted as f of g of x is written as f composed with g. While it is officially read as f composed with g, I like to call it f of g of x because it gives you the idea of what is happening. When I have f of x, instead of x, I have a g of x. So it's f of g of x. I think you should follow that too. And the domain of the composition is set of all real numbers x in the domain of g, such that gx is in the domain of fx. Another important point is that composition is not commutative, which means that f of g of x is not equal to g of f of x. Is not equal to g of f of x. They're not the same. However, in some cases, they might be equal, which is equal to g of x. And in this case, it is called the identity function. It's going to be more clear with the example that follows. We now have two functions defined as one of them is f of x is 2x minus 1, and the other g of x is the square root of x plus 7. They ask us to find f of g of x and g of f of x, and the question whether they form identity functions or not. Let me start by evaluating f of g of x. Now, when I give you a function f of x, let's say it might be equal to x squared plus 1. What do you do when I say f of 2? Wherever you see an x, you put a 2. So you have an x here. You're going to put in a 2 instead of the x squared and add 1. Nothing happens to the 1. You get answer as 5. In the same way, okay? In the same way, when I say f of g of x, it means that if I have f of x as 2x minus 1, instead of x, I put in gx. F of g of x is 2 times g of x, since we replace x with g of x minus 1. And we know that g of x, is just the square root of x plus 7. That is 2 times square root of x plus 7 minus 1. And it cannot be simplified further. Now let's look at g of f of x. We know g of x is square root of x plus 7. Now, when I say g of f of x, I mean to put in f of x instead of x. We have f of x plus 7. And we know f of x is 2x minus 1. We have 2x minus 1 plus 7, which is square root of 2x plus 6. There's not much you can do here. You can take out the 2 and get a root 2, but that does not help you here. This is your g of f of x, and this is your f of g of x. Now, are they equal? No, they're not. This is 2 times square root of x plus 7 minus 1, and the other one is completely different. So yes, we found out these two, and no, they do not form identity functions. I think that was it for this session, and I'll see you soon. Thank you.